All right, here we're going to talk about the idea, the concept of composite functions. First, let me just give you the notation. All right, so when you see this, this is the notation for a composite function. What this means is f of g of x. In other words, the value of f depends on the value of another function, g, and that function depends on x. So here, the value of f just depends on x, yeah? This notation is saying the value of f depends on the value of another function. So where does that come up? What's an example where this comes up in real life? We've all been to a still pond or a lake, something like that. You take a little stone or pebble and you throw it and it hits the middle of the pond or somewhere in the pond, kaplook, and you see these circles spreading out from where the rock hit the water. Now, what is the area of that circle? Well, it depends how long you waited until after you threw the rock. The longer you wait, the bigger the area, right? The area of a circle, we know back from basic geometry or our formulas, the area of a circle is pi r squared. In other words, the area is a function of the radius. The value of the area depends on the radius. So here we've got a function a. A depends on the radius. But as I just said, we want to calculate the area. To calculate the area, we know that we need to know the radius, but the radius depends on the time. Depends on how long after I threw the rock before we calculate the area. So the radius, the area depends on the radius, and the radius depends on the time. That's exactly the idea of a composite function. A function depends on another function. So that's an example of where you could use it in real life. After this, we'll do some examples of using this notation and finding different composite functions.